All right, welcome everyone to the Electric Flight Test Committee of the eVTOL Flight Test Council on Tuesday, April 27th, 2021. We've got a good crowd today, and we are lucky to have guest speakers. And so without further ado, I'm going to turn it over to Al to do a quick introduction of our esteemed guest speakers today from Unisphere. So Al.
All righty. So our guest speakers today are guys that I've known since 2006, I believe. We met in Germany at Grob Aerospace, and the guys were right out of college, and they just banged it out, and we worked together for a couple of years at Grob in Germany. And then when Grob went away, I came back to the US, and these guys launched into a couple of really great adventures. The first of which we're going to hear about right now, the work on the Solar Impulse program. And I think a lot of you are already aware of it in general, and these guys are going to inform us a whole lot. It's stuff especially interesting to this committee. And then later on, I'm going to ping them to talk to us about Unisphere, which is their current company that they founded. And the work that they're doing, again, it completely or largely overlaps with a lot of our interests in things that, even if it's on the edges of flight tests, it's right in the center of our concerns and the various things that they're doing. So these, Christoph and Michael are just all over the place in our interests. So guys, I don't know who is going to go first, but Christoph and Michael, it's your show.
Thank you very much for the introduction, Al. Good morning or good afternoon to everyone, wherever you are. We are in Germany, it's afternoon, and we are really happy to finish the day off talking a little bit about Solar Impulse, take you not on a magic carpet ride, but take you on a solar aircraft ride, and then how this actually transformed into Unisphere, our current company.
Yeah, hello everybody. Thanks again, Peter and Al, for promoting us, but also since I think Al came up with the idea of the eVTOL Flight Test Council a year ago, and we immediately liked it, and we really see much of sense in this council, in this group, in making the eVTOLs at least as safe as today's aviation. So, and let's see how Unisphere can contribute there and give you some insights where we come from and what we learned, and it will be a pleasure. So I'm sharing my screen. I hope it works right away. Done. Share. All right.
Yeah. So we like to take you on a ride today and take you on board of Solar Impulse SI2, the aircraft which flew around the world, and especially like to share a story with you how a digital twin of a flight actually supported or saved the 5-day journey from Japan, from Nagoya to Kalewa in Hawaii of Solar Impulse. Since we're in the vertical flight test council, we thought we'd take out a picture of an aircraft which is taking off vertically here. Dornier 31, just about a few kilometers from where we are right now. It's taking off vertically, but not propelled by electricity. Nevertheless, I think it's a nice picture. A few words about myself. Christoph Schlettisch, 41 years old. I'm an aerospace engineer by education. Was very lucky to get under the wings of Al very early, then to become a flight test engineer. Right now I'm with Unisphere as the founder, and I'm also a commercial pilot for the time being, flying part-time 737s from Germany all the way down to the south into the sun.
Yeah, my name Michael Anger. Anger management is certainly something everybody should know and be aware about when doing flight testing. My background is aerospace engineering and systems engineering. I did the system safety analysis for the Solar Impulse aircraft, and then later on, together with Christoph, spending a lot of time there on the first and second prototype doing flight testing, but then more and more I took over the lead in mission planning, building up the mission team, and in the end for the round-the-world flight, I've been one of the 2 flight directors, Christoph just sitting next to me, solar impulse.
Just a very quick introduction in case you're not so familiar with Solar Impulse. This Swiss project was founded in 2003 by Bertrand Piccard and André Boschberg, and in the end was based in 3 locations in Switzerland. The engineering was in Zurich, the financials and marketing communication in Lausanne, and Payerne is basically halfway in between, in the middle of Switzerland, a major Swiss Air Force base where all the flight testing and the local flights happened. In the end, Solar Impulse was a core team of about 90 people and was funded by over 100 industry and institutional partners. And all of that with the objective to demonstrate the potential of clean technologies by flying a solar aircraft around the world. So Solar Impulse, from the beginning to the end, was a communication project trying to bring renewable energy to the people.
Yeah, some specs are around the Solar Impulse 2 aircraft. So there were 2 aircraft, as I mentioned before, SIA and SIB, as we call them, and SIB, which you see here, roughly the size of an A340, at least in the wingspan, but only the weight of a mid-sized car, 2.5, 2.6 tons, and very little power for this size of an aircraft, comparable to a scooter. You have a few numbers here on the propulsion, 4 times 13 kilowatts maximum continuous power for gondolas and 4 engines. Battery capacity 36 kilowatt hours times 4. Battery weight more or less 1/4 of the overall aircraft weight, as you can see. And a lot of solar cells on top, which created a lot of solar power during the day. And on the battery, especially, and especially interesting for this talk, is that they are passively cooled at that time, so no active cooling, no heat pipes, and so on. Maximum altitude, flight level 280, and descending down as much as possible. We'll see later on. Okay.
Very early in the project, Solar Impulse started to use flight planning tools. The software there was written in-house. It was based on MATLAB, running on local computers, and the software planning tool was at Solar Impulse when I joined already used to verify basic design assumptions, and it was first and foremost used to develop the route around the world. The aircraft started from Abu Dhabi eastbound, ended up in Abu Dhabi, and all of that was already starting several years before the flight. Once we were in the flight around the world, we used the software tool to identify flight windows up to a week before the actual takeoff and prepare the flight. And then in flight, we use the software permanently for flight following, to do replanning if required, and also to support decision making. The software itself was very much focused on the technical details. So every 17,000 solar cell, every individual cell was modeled, every battery cell, the drivetrain, all of that. It was not so much about integrating an airspace structure or air traffic. The only external information which was included was high resolution weather. But things like route planning around airspaces was a manual task, so it was a tool used by the mission engineers and then iterated by them.
Yeah, we have to talk about perpetual flight here because we'll refer to this altitude profile, which is here in the lower left, more often in this talk. So for perpetual flight, the energy storage or the possibilities we used was the combination of altitude, so potential energy, and electrical energy stored in batteries. And to achieve the perpetual flight, it was mandatory to climb to flight level 280 during the day and descend to a lower altitude to reach an energy neutral 24-hour cycle, and this on and on and on. Doing that, we were very limited towards weather changes in ATC, meaning we were very much depending on weather, clouds especially, but also main wind direction, would say, and we could not really go into a vectoring provided by ATC or things like that. We more or less were flying with the weather instead against it. And for this task, we had this mission control center with a lot of people. The mission team itself of 30 people working day and night shifts in the planning and simulation to do all this simulations and details, manual tasks. Yeah. Now, a little bit about this perpetual flight altitude profile or vertical profile. On this graph, you see in blue, the blue line is the altitude flying, so starting from the left 8,000 feet to climbing up flight level 280 and descending again. The green dashed line is the battery state of charge over this 24-hour cycle. And then the gray or brown area left and right is the day and night time differences. So when you start at point 1 with an energy neutral in the morning, meaning you get enough energy from the sun to sustain horizontal flight, maintain horizontal flight, and then you start to charge batteries during the day, meaning the battery state of charge increases during day, and then later on climbing to flight level 280 to reach 280 as late as possible due to the pilot. Later on, a few things about that. And then with full batteries at the same time going to a shallow descent into the night and coming out again in the morning at 0.5 and an energy neutral morning over this 24-hour cycle. Red and green here, just as an additional information, red are features of low clouds at lower altitudes, and the green one clouds above the aircraft, so mainly cirrus clouds, which were also taken into account into the simulation. And yeah, how this looked like in practice, or we could derive some nice visualizations from that, is what you will see next is a map going from Nagoya, so in Japan, to Hawaii, and you will see cloud charts and 2 green dots on the left and right showing the takeoff and the destination, departure and destination, and this little dot in the middle slowly making its way on this 5-day flight to Hawaii.
So what you can see very nicely on the left-hand side in blue is the mainland of Japan. On the right-hand side is Hawaii. And if you watch this green dot carefully, it's flying in between the clouds, sometimes even stopping for a few hours, then accelerating and just negotiating its way to Hawaii in and around all the weather fronts and the clouds. And that's an actual output of the simulation tool we had at the time.
Yeah. And that's, let's say, the starting point for our detailed look at a specific event on this flight from Japan to Hawaii, and where we would like to tell you a few things about batteries in detail.
The actual event had a story up front, and the story actually started with the initial idea of flying directly from mainland China, from Nanjing to Hawaii. And we took off, and about 2 days into the flight, we realized that the weather front just west of Hawaii was increasing in activity, and we would be unable to fly over that front. So we had to divert very quickly towards Nagoya in Japan, which at that time was luckily still in reach. And as this was more or less an unplanned diversion, the aircraft arrived there in the late evening hours, and the ground team with the mobile hangar and all the supporting equipment was still in China, fighting the logistics and the customs, and the aircraft had to spend the night in the apron in rain. And when you see the picture above, you see the ground crew inflating the first segments of the mobile hangar, and you can see the puddles of water of rain from the night before. And obviously, this aircraft Solar Impulse was not really designed to take rain. So as a consequence, there was extensive work done and inspection by the engineers. Replaced also a few items of equipment, and this mandated a maintenance flight. Now, getting the approval out of Nagoya to fly a maintenance flight in the middle of the busy Japanese airspace was impossible. And as a result, we ended up in a situation where we had to piggyback this maintenance flight on top of the actual record-breaking flight from Nagoya to Hawaii. Meaning we had to do test points from the maintenance flight, and if they were successful at the success gate, then continue all the way out onto the Pacific. So that's the story leading up to the actual event.
Can I ask what the critical test point was and what you would have done if it had failed?
It was several test points, and one of the main objectives was to cold soak the aircraft for a few hours at flight level 180. And if this would have failed, we would have returned to Nagoya. This was planned in that way. However, we believe that this would have saved the aircraft, but maybe jeopardized the entire project due to political issues in Japan. So there was also a project pressure, but I would not say that this would have had an impact on the outcome of the maintenance flight. This was a purely engineering task. But if you look at this chart here, it shows the routing to Hawaii. And when you have a look at the color coding, just imagine it say everything which is blue is close to the water, the blue ocean at low altitude. Everything in red is at high altitude close to the sun. So once you see that color coding, you get an idea about the 5 days. And the actual problem, which ended up overheating the batteries, was this little part of yellow just to the south of the November from RJNA. The first part of the flight was actually the thing which we didn't really comprehend at the time. This was the maintenance flight. What you see here again is this altitude profile taking off, but now the maintenance flight mandated this cold soak of 4 hours at flight level 180, and we suddenly had this tableau, this little table where we had to get up to high altitude very early. We did the test points there, we did the cold soak, everything was fine. We passed all the decision gates, and we were quite happy to finally go out on the Pacific. And for pilot comfort, because it was the first day of a 5-day non-stop flight, we decided to descend from flight level 180 to flight level, I think, 110, to go below the altitude where you need oxygen, to go in warmer air, and basically keep our pilot happy. And this descent there was more or less in the middle of the day, where we reduced the engine to idle. And obviously, as we were planning to head out on the Pacific, the solar generators on, and this resulted in a very high current, charging current into the batteries. Something we never had before, because we never flew these descents at daylight. At that time, we were quite happy, and we happily set course east with the maintenance test flight completed and the aircraft disappearing in the evening of the first day.
Yeah, so we were, let's say, all good to go, set course east, and then in the morning of solar day, we were talking solar days there, to our electric and propulsion team reported, well, yeah, you know how engineers are, and they raised concerns about the battery temperature, but it was more severe than we initially thought. So we were actually at, as you can see in the chart, we have passed the PNR, the point of no return, and we're already in, let's say, just before climbing on the next solar day, and the battery temperatures were already quite high because of this maintenance flight, because we were having solar generators on when descending and go back with full throttle, on zero. And so the charging current was super high into the batteries, and then heated up the batteries significantly. And the remainder of the flight was also be subjected to ISA plus 20 conditions, and with the profile we had in mind, the batteries would overheat in 3 days from now. So just before Hawaii. So meaning we would have to act because the caution or corrective measures would have been initiated at a temperature of 60 degrees centigrade.
So what we saw there, we took the actual conditions of the aircraft at the time. We ran the simulation, and it showed us at the second day of the flight that we would have a problem on day 4 to day 5 and would not make it to Hawaii. And as a result, I mean, the entire strategy changed. We had to save the aircraft, had to save the pilot, and we had to actively manage the charging and discharging current into the batteries, keeping it as low as possible while still maintaining this altitude profile over 24 hours.
So there was no way around charging the batteries because we needed them to achieve perpetual flight, and then suddenly we had to, let's say, optimize the smoothing of the charging current, because the temperature increase was proportional to the current going in and out to the battery. So what we tried to do by flying faster, by climbing earlier, is to smoothen the charging current over the whole day, that we were still able to fill them up to 100%. But this altogether was very complex to manage, all these dependencies on energy, altitude, ground speed in the end as well, so that we once more had to, we digged into simulation to solve this complex task, and re-simulated several options, and finally successful. But how?
What you see here on the right-hand side is a plot of the battery temperatures for different colors for batteries, and the grayish areas below are the energy produced from the solar generator. So you can always see that the battery temperature increases when we charge the batteries on the upper flank of these grayish areas. And on the second day, the gradient was a lot higher than on the third day, where we started to manage, and on day 4 we had learned even more how to manage it, so the gradient got even lower. And we were able to reduce the daily temperature increase from 5 degrees to 2 degrees on the battery, which enabled us to fly the 5th day without reaching the limit, but we would not have been able to fly a 6th or 7th day, so we barely made it to Hawaii. And all of that was done doing, I don't know, hundreds of re-simulations all the time to verify that we can still make it.
Yeah, and we all know the end. We finally approached Kalaeloa in Hawaii with this record-breaking flight, taking 170 hours and 52 minutes. With these nice impressions we got here from with the surfboard girl in Hawaii, and it was a great flight and a great achievement for the team.
But it's only the first part of the story. The aircraft landed, everyone was happy, obviously, very proud. The engineers started to deploy post-flight checks, and they showed unusual battery behavior. And somehow we were a little bit puzzled, because we thought we did everything right, we managed it well, and now batteries are behaving strange. It was the beginning of an extensive discussion, exchange of theories and ideas with the supplier. And actually it turned out that the battery temperature limit was valid for mean sea level, but not for flight level 280. So apparently it is the same physical behavior as they have at the boiling point of water, that your batteries boil at a lower temperature at higher altitude. And it should have been around 40 degrees for the batteries. We flew it at up to 52, so we basically boiled all 4 batteries all 4 days without knowing. And we're quite lucky to have it made to Hawaii at all. And as a result, the picture on the right-hand side shows the aircraft being stripped and prepared to stay in Hawaii for the winter from 2015 to 2016. And we continued the flight around the world the spring of 2016.
Yeah, as a consequence of this, certainly we took out a few lessons learned and actions. So one of the things the engineering took away was that they redesigned the battery housing, where they included an active cooling system with basically inlets which could be opened and closed during flight. And this cooling effectiveness was tested and modeled in flight simulations as well, but also small wind tunnel tests. Then we integrated a strategic schedule into the simulation you see it in this graph below, where we have these trigger points for battery cooling off or the battery cooling on. As part of the simulation strategy into this digital twin.
What the battery cooling allowed us to was to fly missions which were further away from the design mission. If we would have just flown design missions day in, day out, the passive cooling would have worked. But the moment you go out of the design mission, you end up having slightly different requirements and limits. And this was also a reason to, let me see if we go one slide ahead.
Sure.
That we went back to all the flight logs we had from previous flights of Solar Impulse, and we created so-called footprints. So we took a lot of different parameters, simple ones like altitude, temperature, but also battery current, cloud coverage, humidity, and basically created footprints of flights where we have been with all these parameters. And then running simulations of future flights, we were able to see if we are well within the envelope of all these parameters, or if certain values went out of the domain to which we were used. And this gave us an early indication to if we end up in like new situations which are further away from the design mission for the aircraft.
Let's say we did kind of machine learning, ML, which at that time was manual learning. But we took all the recorded data and tried to, and this is just a few examples here, but basically apply in each planning, in each simulation of future flights to see deviations to the known envelope, and raise awareness in the team. And here we see, for example, battery current on the left graph, again a little bit higher to what we knew, to have the electric and propulsion team monitoring that a bit more closely during flight.
Did the cooling system plus that analysis enable you to broaden your flight envelope for the rest of the flight?
It did enable us to broaden the temperature envelope of the battery. It was just basically a NACA duct you could open, and the air was going to the batteries, but it was also pretty difficult to manage that versus the outside air temperature. If you have 30 degrees OAT and the battery is at 35, you don't get a lot of cooling. So you have to do that at higher altitudes or at higher speeds. But it did not open the envelope of the aircraft. It gave us the opportunity to be more aggressive with current in and out of the battery, which in a way gives you more options if you plan a mission to be more aggressive in climb and also in descent, and be less restricted on these batteries.
Sorry, most trouble. Yeah, then we finally succeeded with the completion of the round-the-world flight in 2016, summing up to 17 flights in total, flying through 7 countries, a lot of records and a lot of solar energies stored or produced with the aircraft. And basically, we had to celebrate. What you see here is the Mission Control Center, which was hosted in Monaco, and the full team there in Monaco. And that actually was the point, or the end of the successful end of Solar Impulse, with the completion of the round-the-world flight, was the starting point of Unisphere. On the left, you can see this little picture with we flew 40,000 kilometers with our view. Take it further, and actually, what Christoph and myself did, and a few other folks from Solar Impulse, we founded Unisphere and take it further there.
The Solar Impulse project was never intended to have a commercial spin-off. So it was just a Marcom project in the end, and we had so much ideas or so much knowledge there, know-how, how to do flight management, how to build a flight simulation, that this was the beginning of of Unisphere. And what we do with Unisphere here, it's 3 more slides before we answer the questions, is that we want to help the automation of unmanned aviation. So on the left-hand side, I don't think that we have to talk about that guy. In the middle, we see the typical airline pilot who is still in a domain where he is in charge of everything, supported by technology. And on the right-hand side, this is where we all want to go in the near future, that we end up in a very highly automated way of operating preferably unmanned aircraft. And all of this that requires the automation versus with an autopilot, but also of all the processes and procedures around.
Yeah, with the main challenges, I think you are most aware about them as well. The sheer number of unmanned aircraft systems, including drones, will increase by a factor of 500 compared to conventional aviation. And public acceptance certainly is key. So meaning safety cannot be traded. The public expects the same safety level, and eVTOLs as well as the drones are operating, let's say, in a challenging environment, meaning close to the surface, maybe behind buildings, and so on. The electric propulsion as such is relatively new to aviation, and looking from the small drone to the eVTOL, they all have their fights with these new technologies and their unknowns. And on top of that, there is this automating factor where all pilot responsibilities, which are a crucial safety layer today, should long-term be automated. And that's what we are driving for.
So what we have developed with Unisphere is a digital twin of a flight. We start with the 4D trajectory, which is basically a flight path over time, but it includes a lot of additional information, data, and parameters. So we include performance models from very simple one up to very detailed and explicit ones, as we had for Solar Impulse. We model your aircraft limitations for the aircraft, can also be for the sensor or even for the payload. We include high-resolution worldwide weather data, and we can include also air traffic information. And all of that can then be optimized, let's say, for minimum flight time, for minimum energy consumption, and create a data set which is a very accurate and relevant representation of a flight of a drone or an air taxi.
Yeah, and this, what Christoph just explained, is more or less the left box with the digital twin of a flight. On top of this, we add we digitalize pilot know-how, meaning we integrate also the common operating procedures, let's say, which are indoctrined by an airline operator. We can set operational limits, we can do evaluations along the flight path, and partially automate the risk assessment of a flight. So meaning I have a lot of parameters which are looked at by the system, and if they are all close, let's say, to the caution, then the flight has a higher risk than if they would be very far away from the caution. And on top of this, especially important for the eVTOL era is the customer experience. We call that ride factor, but certainly the customer is eager to fly in calm conditions than in very gusty ones. And both boxes together we call the smart 4D trajectory, which long term will enable automated flight operations.
Yeah, all of that is running in the cloud. It's running today. It's a set of discrete event simulations in microservices. This is set up in a way that it can scale with the number of requests. It is agnostic to the cloud platform and accessible for our customers as software as a service or by API. And right now with Unisphere, we are 4 years old, about 10 people, and pretty proud to have companies of drones, air taxis, and high altitude platforms already using this trajectory simulations in Germany, in the European Union, and in the US. And actually, Mijing made the calculation this morning. It said was just estimating, and we see that we do 24,000 flight simulations every day. Last slide is just once more. Oh, okay, you're missing one. Anyway, then I go to this slide.
This one?
Yeah, the little boy, the little rocket man, we call it. It's basically with Unisphere, we have built on the experience of Solar Impulse, which showed Michi and myself very well that if you want to operate innovative aircraft, you have to be prepared that something happens which is out of the normal scope you have as a pilot or an engineer, and that you need the technology to help you make that step to bring these things in the air, and as soon as they fly, obviously you want to commercialize on that.
I would like to quickly go to that slide, which we were obviously missing here. Let's see if it's...
I think it's like 26, Michi.
26. Give me a second.
Yeah.
26. Okay, it's hidden. Can you see it now?
Yeah.
Okay. Actually, the digital twin of a flight, we think, yeah, we do derive several services out of that. And first of all, you can use a smart 4D trajectory on a very strategic level, meaning you can do studies of commercial viability of route networks, for example, or operational analytics in general, before you go actually into a pre-flight phase. In the pre-flight phase itself, the system is doing service availability predictions, so meaning it uses a network and detects potential flight windows. This is for example, used by some eVTOL companies in the flight testing domain, where they want to find very specific conditions and detect over the next 7 days when there's a suitable windows to fly. And as a second thing, we can derive an OFP certainly out of that, so a flight plan, including alternate strategies and calculations and all the contingency calculations. You can derive from that strategic separation topics like airspace reservation, ATC flight plans, and also we are, as the system is quite fast in calculating, we can also include last-minute changes just before flight. And in flight, certainly the OFP is a prerequisite for a real-time deviation monitoring, and then for an in-flight replanning and decision-making. Post-flight, we aim for a safety management system which offers a auditable flight documentation. And then you can derive more things like predicted battery state of charge at landing, with what kind of state of charge would your next flight start, how much do you have to recharge, and so on. And the digital twin itself certainly allows a lot of, generates a lot of data for analytics and optimization. And now I'm jumping back to the last slide.
Yeah, so that's basically our short presentation taking you on the Pacific Ocean in the electric aircraft trying to handle for hot batteries. Thank you very much for the attention. And I think, Elle, I already see 3 questions, but I'll leave it up to you if you want to do the Q&A right now.
Yeah, we'll go ahead and do the Q&A now. So I'm looking at the chat. So Dushan asked how much the cooling ducts contributed to drag.
I don't know, to be perfectly honest. The cooling ducts were NACA ducts, the one you have on your, let's say, normal 4-seat airplane. So I assume the overall contribution to the drag was not very high. Again, it was also used just, let's say, a few hours during the course of a 24-hour cycle. And the weight of it, I mean, all the ducts itself was rapid prototyping, so really lightweight. The most heavy part was actually, if you remember the picture from the outside, motor gondolas. There was like a Bowden cable, I'm not sure if that's the right word, going all the way to the pilot to give him a mechanical option to open or close these battery coolings, because any electrical system would have been an issue in the system safety analysis. So the most heavy part was the actual linkage from the cockpit all the way to the outer and the inner gondolas. Overall, I guess all the 4 cooling units together, I don't know, maybe 4 kilograms, yeah, maybe even less. So really, not so much.
Excellent. So Virginia asked, how much did the Ground Operations Center rely on the pilot to make the control inputs when you needed to change the flight procedures? Or how much was autonomous versus pilot input?
We had a stability augmentation system, which basically was capable of keeping wings level. But let's say all the departures, all the arrivals certainly were flown manually. And then for convenience, yeah, in calm air, they could use the stability augmentation system. But I would say in terms of 50-50 in terms of flight time, so 50% at the controls and 50% on stability augmentation.
With regards to the changes in the flight procedures, all the manipulations we were simulating and suggesting had to be executed by the pilot. Mm-hmm. So the aircraft or the pilot was actually able to fly the aircraft fully by himself. There was no way or means from the ground to, let's say, bypass the pilot and manipulate the aircraft. And in the end, this is also a safety topic. A pilot should be able to do the flight. What the pilot was having problems with is to, let's say, comprehend on day 2 that he would have a temperature problem on day 5. But the actual short-term flying up to, let's say, 24 hours in the future could be done by the pilot completely by himself.
All right, so Tom asks, and this is relevant to the working group we're working on, how did you track in your simulator? Let me back up. I heard you say that your simulator kept track of thousands of individual cells in the battery packs. And so Tom's asking, how do you actually track that performance or model that performance or simulate that performance and use it in your planning, both on Solar Impulse and with Unisphere, now that you're offering this as a service?
The modeling of the battery cells is something we've done to great lengths at Solar Impulse, and it's in cooperation, let's say, with the aircraft manufacturer, with the supplier, taking the data either from the supplier or even from test bench, tests of individual cells, and then how you track them in the simulation. I'm not sure if I understand the question correctly, but tracking the batteries to me sounds a little bit like configuration control. That I know which cells are packed in which battery, which is in, let's say, which airframe at the time, and then how many flights or cycles or did it do. And this is a tool where we have a how do we call that?
Life cycle management?
No, the configuration manager, no.
Asset management.
Asset management, yeah, asset management. Basically, where you can set up a database and starting very, very big, having an asset airframe 1 or aircraft 1 and 2, and then you can break it down to airframes, to motors, to batteries, and manage that. But in the end, we are relying on the level of detail in the performance model and also on the data we get from the telemetry of an airframe. So if the airframe provides individual battery cell voltage, we can do something with it. If this is not provided in the data, then this is then beyond our capabilities.
Okay. Herb asks, how easy is it to connect the post-flight data to a systems analysis, an aircraft design module?
Not easy because it's individual. Yeah, it makes all the sense in the world to do that, but we don't have a interface which is standardized here. If there is a request by a customer, obviously we can accommodate that, but we have to look that up in a detailed.
What we partially what we have started a few years ago was that we derive from recorded flight data, and this is now applicable for drone delivery service of about 17,000 flights. We derive or we re-engineer a performance model out of recorded flight data. As you can imagine, the drones are not tested until the edge, and there's no real performance model there. So, but what they have, these startups, is they have a lot of flights. So what we're building at the moment is a concept in deriving a performance model based on a lot of data. We could call it big data or machine learning, but we are not that, let's say, obsessive in that sense. But we call it engineering for the moment. But what we do is we derive a performance model based on measured flight data. I don't know if this would apply for eVTOL world. I don't think so, because the eVTOL world is more like they have the certification standards and they have to, let's say, much earlier before flying, prove to the authority the concept of battery management and the whole aircraft performance and do wind tunnel testing and analysis and so on.
All right. Herb also asked if you could integrate an aircraft design module with your tools today.
We certainly see a lot of value in that, but on the other hand, I have to admit we never did that. So this is something we would have to discuss with the manufacturer, with the customer, one-to-one. But I definitely see the value in having a feedback loop into the design of the aircraft from either historic flights or also a lot of flight simulations.
What we are, I'd like to add one sentence on this. What we are really good at is, let's say, doing route network analysis and have a certain aircraft system with certain capabilities designed, and you can run that with using historic weather data over the last 3 years, for example, on a very specific route, and then find out about the actual operating conditions you are about to meet in real life. And then derive from that whether you need a de-icing system or how often you would need that, and which location is the best location to start an air taxi service. Is it what's better, San Francisco or LA? I don't know, but we can find out using the data. Yeah.
So, in your experience, gentlemen, if you're doing a system safety analysis of an electric eVTOL, um, what is the big bar on the Pareto chart of risk sources?
Mm,
It's a good
good
question.
question.
Risk sources.
Is it battery management software? Is it cell chemistry in the batteries?
I think it's common mode failure. Something like you have a driver for your all your electric engines, and they run the same software, and they all crash at the same time. So when you start from the functional hazard analysis and you take this as an input, all engines off. So yeah, that's I think a big deal for eVTOL.
Okay, very good.
And battery chemistry is probably more like a question of the performance of your eVTOL, if you can make the range or these things, but probably not necessarily the biggest risk.
Okay, very good. Well, we have time for one more question. So does anybody else have a question? Feel free to just unmute and ask directly if you like. All right. Well, in that case, I'm going to say thank you to Michael and Christoph. I found this terrifically informative, and I totally see the value of what you guys are doing at Unisphere.
Thank you for just having us and giving us the opportunity to present in front of knowledgeable people. That's always a very, very nice thing. And yeah, thank you.